Good morning, or aloha I should say. This morning's topic is about tsunami forecasting, and this is forecasting after an earthquake has generated a tsunami. It's not about forecasting when earthquakes will occur in the future. And I think this story originated about 25 years ago when the state of Hawaii was put into tsunami warning in 1986 from an earthquake that occurred in the Aleutian Islands. And at that time, we had no idea of being able to determine what was between Alaska and Hawaii. So the conservative approach was to call a warning and evacuate all of the islands. Well, a little 6-inch tsunami showed up on Waikiki, and the state of Hawaii Civil Defense Director, Mr. Price, took NOAA to task of, well, why are you evacuating this beautiful state, interrupting people's vacations, and an economic loss of about $70 million for a false alarm. Well, that was the problem. How do you distinguish between a non-destructive tsunami and a destructive tsunami? So that's the story I'm going to tell you. It took place over 25 years, and this organization, MTS, played a key role in getting the right people together on a continuous basis over the last 25 years. I'd like to give credit to the people who helped contribute to this presentation, Vasily Titov, Rachel Tang, and Yong Wei at the NOAA Pacific Marine Environmental Lab in Seattle, Washington. Okay, so I'll talk briefly about history, testing, and evaluation of this technology. Then we'll jump to the 2011 tsunami and show how the system worked, and then we'll talk a little bit about the future. Okay, so brief history. Started with technology to detect a tsunami in the deep ocean. The thought was that by measuring the pressure on the seafloor, because you had a stable reference, you could detect a tsunami in the deep ocean. And that was not demonstrated until about 1990, when there were several instruments out there that we thought could detect these tsunamis 1 centimeter or so in the open ocean. But it wasn't until about 1990 that we had enough evidence that this would actually work. Then the problem was, how do you get this information from the seafloor to the warning centers? So then this is a technology conference, so getting information acoustically from the seafloor up to a surface buoy via GOES satellite to the warning centers. That was the first generation of this DART buoy. It took about 10 years to develop this and to make it work, and a prototype was online in about 2003 when it was, and this is the way it looks. Oops.
The DART tsunami detection buoy is deployed in the open ocean from a ship. When an earthquake generates a tsunami, the magnitude of the resulting tsunami wave is measured by the tsunamometer and transmitted via satellite to the tsunami warning centers, where it is used to improve the accuracy of the tsunami forecast.
So that was the first generation. And in 2003, this technology was transferred to an operational unit in NOAA called the National Data Buoy Center. And they had these instruments operating in 2003. When we detected, 2 months after it became operational, we detected another earthquake, another tsunami generated by an earthquake in Alaska. And this time, the tsunami was about 2 centimeters in an open ocean. And because of that small amplitude, there was no warning issued for the state of Hawaii. So that was the first demonstration that this particular technology could be used in avoiding false alarms. However, on the north shore of Oahu, we had an unusual surge of water that was much higher than we had expected. And so what our assumption was that if the threshold of that tsunami was less than, say, 3 centimeters, we didn't have to worry about it. That theory was blown out of the water because here we had an example of one that was lower than that did cause some damage. So the next generation was a two-way communication that not only brought the information to the satellite, but you could talk to the buoy on the seafloor. And one of the clever distinctions about this is that one of our key engineers, Scott Stalin, thought, well, you know, if you could talk to it on the bottom, you know how computers often just stop working and you have to reboot them? So guess what? He put in a little feature that would reboot the system on the seafloor. And it turns out that that has saved operationally millions of dollars, because they do, although these processors are quite reliable, they still sometimes do unexpected things. So this is two-way communication. That means that now you could query the sensor anytime you wanted to, no matter what, and you could detect it any amplitude you want. And the bonus was it gave you an operational tool. And so that was online immediately following the 2004 Indian Ocean tsunami, when a huge influx of money came and allowed NOAA then to take this operational array, which was about 6 buoys, and then deploy 39 in the entire Pacific. So we didn't stop there. The next generation was, the next problem that was encountered was the cost of these buoys. As Marcia pointed out, these are expensive devices to put buoys on the seafloor. In the open ocean, and maintain them. And one of the most expensive parts of that maintenance program is the ship time cost. And so the concept was that we should be able to deploy a buoy off a smaller ship, say a fishing boat. And if you could do that, you needed a device that basically would self-deploy. And so this is called an easy-to-deploy version of the DART. And it works the same way as the other DART, the larger DART buoys. But now this one simply uncoils the line, and when it gets on the seafloor, that's all in one unit, then the sensor is part of the anchor system. And that allows then the ability to deploy these buoys with a smaller vessel, thus reducing a lot of the cost. And at the same time, there was effort put underway of sensor reliability, as Marcia talked about, where these would last about 4 years, so that they would become basically expendable. In the course of 4 years, you know, technology refresh, you basically can't get the components that you could get 4 years ago. Okay, so in a short amount of time, in about 15 years, $10 million was spent. There are 2 patents, 3 generations of DART technology, 3 transitions to no operations and 1 to industry, and 1 commercial license. That's sort of the technological advances that have been made using this form like MTS. And as a result of that, we have a global array of these sensors now that can detect tsunamis throughout the world's oceans. And all the red, this is a global tsunometer network, and the National Data Buoy Center makes these data available to the world globally free of charge. And this is the array as of September 10th. And if you notice, most of them, the red ones are the US, Australia, Chile, Indonesia, Thailand, and Russia. And that's quite an accomplishment, I think, in getting the cooperation of the world in addressing a global problem. And also, a byproduct of that is because of this technology was developed in a cooperative fashion, it became the gold standard of the actual scientific standards of the world. And since that time, since 2003, 40 tsunamis have been measured, and I think a lot of credit goes to the National Data Buoy Center for making these reliable buoys and the data available to the world. Okay, now you have a sensor. But the idea was, as Mr. Price said, do we have to evacuate or don't we have to evacuate? So this is what the system we came up with, was that if you look at all the subduction zones in the world, which are generally the problem of creating large earthquakes that generate tsunamis, and these are the historical tsunamis, you see you've got a global problem. And so the idea was, could we detect the tsunami within an hour of generation and then take appropriate action? And that's where this new technology that I've described is put into play. The sensors, we're not doing this just for having some cool technology, we're trying to forecast how big the tsunami will be. So here are the tsunometers, and we've gone through those 3 generations. And then how do you model something like this? How do you forecast it? So the next step is to have pre-computed propagation models in place so that when the tsunami occurs, you have this pre-run capability in place. Because in the open ocean, the tsunami is more or less a linear problem, and an inversion works very cleverly for that open ocean propagation thing. But once a tsunami comes into shore, it becomes very nonlinear. And it's at that point you have to bring in high-resolution inundation models to find out if it's going to flood or not, which is the forecast problem. And then you need to test it. And since that time, because of the reliability and the data, we've had 17 real-time tests, 13 data tests, and over 30 global events that have been testing the system. So we're building up the reservoir of knowledge and experience to see how well this works. So we'll just keep So the history of the modeling is about a 12-year R&D effort. It would cost about $20 million. There's one copyright of the software. 65 inundation models have been developed, validated, and transitioned to operations, 2 transitioned to operations. And now there's a web-based or a cloud version that will be under development, which will be shared by the world. So the characteristics of this forecast system are free, shared data in real time provided by NOAA, National Data Buoy Center, a free access to modeling technology provided by NOAA PMEL, and training on modeling technology provided by NOAA PMEL. So this is the forecast system that's been created. So now let's take a look at how it performed during the Japan event. But before we start on the technology side, I'd like to take a few minutes to show you a video of some of the actual footage during the tsunami, and I'll be making comments along the way. So notice how these homes are lifted up with the buoyancy of the water, and then they become floating objects, debris. Same with automobiles. Here we have fishing boats. Notice that the microwave tower, which has a small footprint, remains standing. Here's a reinforced concrete structure. They generally survive tsunamis. And of course trees, which have small footprints. Here's some more towers. One of the aspects of tsunamis that's not commonly understood is the flooding problem with fires. This is typical in a developed country where you have lots of combustible material near the coast. So you have flooding and fire simultaneously. Notice the whole city. It's just crumbling before our eyes. Now, one thing you will not see in any of these are people. In the Indian Ocean tsunami, a lot of people caught in the water. The Japanese prepared, evacuated like they were supposed to. And as a result, over 90% of the people who could have died in the tsunami survived. Tragically, 10% did not. there, but I wanted you to sort of try to grasp the significance and enormity of this. The vast majority of the damage was done by the tsunami. Of the homes that were all built according to the seismic code, of course, didn't survive the tsunami. Possibly the worst tsunami in Japan's history. In 1896, Henriku, in the same area, 22,000 people died, but there was a much, much smaller population. It's estimated 22,000 people were dead, and are still missing. $215 billion in damage. 620,000 homes destroyed. 350 ports and 18,000 fishing boats damaged. This is an enormous problem for this country, for the Japanese, but it's an opportunity for us to look at how the system we developed for forecasting worked during this event. So here's the system that I described earlier. Here's the offshore buoys. 3 of them are owned by the U.S., 1 by Russia. The earthquake occurred right here at the grid where we had done these forecast models. This is the subduction zone. So everything was in place prior to the earthquake. Bingo, the earthquake happens right here. Within 30 minutes, it was picked up by the first DART station. All 4 of these buoys were working. Largest tsunami ever recorded in deep ocean, 1.64 meters, was captured within an hour. But the second buoy up here detected it. It was a smaller wave at that time. If you took both of these first arrival times and inverted this signal, then we came up with the initial estimates of what the source looked like, and it was something like this. It was 400 kilometers long and about 100 kilometers wide. Each of these little squares are 50 by 100 kilometers. So that was the initial source. Then the model was run in the forecast mode, and then when it arrived at these other 2 DART stations, one south and one north, it was a very good match. So it was constrained on both the western side, north and south sides, and when you have 3 sides of the source constrained, you feel good about the results that you would get. So this is what it looks like, vertically exaggerated. This is about a 10-meter uplift. So it's a dipole with a big lift up on the eastern side and a drop on the western side. So there's a big hole in the ocean approaching the coastline. This is what it looked like after 30 minutes. After 1 hour, it had reached the second buoy. And then, as the wave was propagating, it went over these 4 buoys. That was the first thing. And then, as it hits the Emperor Seamounts, notice the reflected waves coming back. And then it hits the Emperor Seamount chains. See all the scattering from these underwater topographic features. The wave keeps going and refracting and reflecting once it hits the big coastlines like the west coast. It just enveloped the Hawaiian Islands after about 7 hours, about 9 hours on the west coast of the U.S. About 12 hours is along Mexico, and starting to enter the New Zealand and going into the Indian Ocean. By 15 hours is approaching Central America. And then after 24 hours, approximately 24 hours, it had completely propagated across the Pacific Ocean and created damage down here in Chile. Now, this is a fairly complex wave field, and one way to simplify this is to think of an energy map, and that's just to take the maximum amplitude of any of those grid points and plot them on one plot. And you see here that the energy was basically distributed according to the topographic features it encountered. Like, for example, the Cape Mendocino Fracture Zone acted as a waveguide. And that brought energy up here, all the way over to the west coast of the United States, where there was damage in Crescent City. Another lobe of energy hit Kahului, where there was some flooding. Hilo's, not much flooding, but along this coast there was some flooding. In fact, last night where we were having the reception, the tsunami actually had come up almost to that platform. It had flooded several of the steps that were going down to the lagoon. So then, The comparison was made with the other DART stations that were working throughout the Pacific, and there was nice agreement, so it looked like the forecast model was behaving properly in the open ocean. And now we'll take you down to the forecast for Kahului. And I want you to focus on, there are 4 stations here. We're going to focus on Kahului, and the tsunami's coming in. Kahului is on the island of Maui, and it's right here, because it was flooded. And before the tsunami arrived, the evacuation order was given, and if you watch this little yellow ball, you'll see the tide gauge, which is indicated by the blue, and the red is the model, and the tide gauge is located right there. You can see the first wave came in at about 6 feet, then it drained down 6 feet, it went up 6 feet, so you had about 4 cycles of this 6-foot wave coming in, draining the bay, filling the bay, draining the bay, and this is some drainage taking place where it exposed the seafloor. And then after about 2 hours, it was all completed. This occurred at 3 o'clock in the morning Hawaii time, so it was pitch black. Nobody could see this process as it was happening. But I'll show you a video that was taken following this the next morning. This was a forecast for Kahului. Here's the harbor. This was forecast to be flooded. And then the next morning, a helicopter flyover, and I'll show you. It started right here. Now it's looking at this little port area. Here's the concrete barriers. So when we compare the flooding that was taking place versus the evacuation area that was established many years ago, as Brian mentioned in his opening remarks, they evacuated this entire area, and this particular event was not going to exceed that flooding area that was estimated. So this shows you the robustness of the evacuation maps that are in place for Hawaii. Okay, so then the thought was, okay, it worked pretty well for the distant tsunami problem, but the Japanese had this immediate problem. How, if we use the same approach, could we apply it to the local tsunami problem? That's what we've done in the hindcast experiment that I'll now show you. And basically, here's the same source, and here are 8 offshore buoys that are called GPS buoys. They can measure the tsunami close to the Japanese coastline. These data were not available in real time, but in hindcast, using the same source that we used to forecast the Kahului flooding, we then compared that to the 8 offshore gauges and got very good comparisons. Here was a maximum about 6 meters, and this was in roughly 200 meters of water. So a very good, so we had some confidence that the model was working. Then if you take it down to the resolution of 50 meters along the coastline, the black is the coastline, the pink is the maximum extent of inundation as measured by all the scientists in Japan and throughout the world who came to the surveys, and the brown is what the model forecast. So let me blow up a couple of areas around Sendai. You can see that this particular technology worked pretty good. It underestimated in this, the model overestimated in this area and underestimated in this area, but by and large, pretty good agreement. So it looks like using this technique, this would be a viable way of having a local tsunami forecast delivered on the order of about an hour. So the future is that for distant tsunami problems, which is the problem that Hawaii posed 25 years ago, was that we can now forecast flooding with an accuracy of about 80%. And in this period of time, 3 false alarms have been avoided. But for the local tsunami forecast problem, this is the really breakthrough, we think, is that the hindcast shows that local forecasts are now possible within about an hour. So the earthquake shaking is still going to be the first indication that a tsunami's happened, and then people will have a forecast. And as a result of this large tsunami, there was a workshop held yesterday, and one of the recommendations is the establishment of a local tsunami testbed for research and technology. So MTS still continues to contribute to this problem. Mahalo.